Good morning to our respected principal sir, Professor Gyantosh Kumar Jhas, IQAC coordinator and webinar committee convener, Dr. Binita Tuli ma'am, esteemed guest speakers, Dr. Saurabh Kumar Singh and Dr. Mahendra Kumar Verma sir, teacher in charge of Department of Mathematics, Mr. Kapil Kumar, faculty members, students, and dear participants. Sorry. Now I am Ravinder sir, am audible?
Yes sir.
आप अनम्यूट करिए खुद को.
Yes sir, I am unmute. Ravinder sir, I am audible?
Yes, yes.
Thank you sir. I, Anil Kumar Rajak, on behalf of Department of Mathematics, ARSD College, welcome you all for the national webinar.
Anil sir, your internet is fluctuating.
There is coming a problem from my side. This is IQAC and Department of Mathematics. This next webinar is organized to celebrate the Mathematics Day 2022. As we all know that National Mathematics Day is celebrated every year on December 22 to honor a very well-known famous Indian mathematician Srinivas Ramanujan, who was born on this day in 1887, and he contributes to mathematics. This special occasion, first of all, I would like to thank our honorable principal sir, Professor Gyantosh Kumar, for his giving us this excellent opportunity to organize national webinars for the benefit of faculty and students. So now I request to our principal sir to welcome our guest speaker and say a few words. Principal sir. Principal sir. सर मेरी आवाज आ रही है?
अनिल, Ravinder.
Yes sir. I think Anil sir, your voice is not coming. Net is fluctuating. Is there anyone else from the committee who can take over? Kapil sir.
Chhatrapal sir, I have sent you the file. Please you continue. Sir, there is some problem from my side in network, so please you join.
Now your voice is clear, Anil. Now your voice is clear, but
Yes, sir.
earlier.
Yes, sir. Sir, so sir, please you welcome sir our guest speaker, and after that you will continue, sir.
Okay. Good morning to all. Dr. Saurabh Kumar Singh and Dr. Mahendra Kumar Verma our guest speakers for this national webinar. IQAC coordinator, Dr. Vinita Tuli, Mr. Anil Kumar Rajat, Mr. Kapil Kumar, colleagues and my dear students. It is a great pleasure and honor for me to welcome both the speakers in this national webinar on the topic Ramanujan, a great mathematician. And as Anil has spoken, that every year we celebrate the birth anniversary of the great mathematician Ramanujan in our college. And this year we are celebrating this program in online mode. I'm glad that students of mathematics would be definitely benefited from this webinar, and they will get more information about Ramanujan and his theorem. So once again, I welcome you all, and Anil and Kapil, you are doing a good job. So all the best for organizing this webinar. Thank you so much. Over to Anil.
Thank you, sir, for your motivational and encouraging words. Under, sir, your dynamic leadership, our college has ranked 7th in NIRF in 2022. Thank you so much, sir. So now for this national webinar, we have two sessions and two eminent guest speakers. It is my honor and immense pleasure to introduce our guest speaker, Dr. Saurabh Kumar Singh, for session 1. Dr. Saurabh Kumar Singh, working as an assistant professor in the Department of Mathematics and Statistics, IIT Kanpur. He received his PhD degree thesis entitled Some Problems in Number Theory under the supervision of Professor A. Shankar Narayanan from the School of Mathematics, Tata Institute of Fundamental Research, TIF. My voice is coming, sir. Can you confirm?
It is
Voice
breaking.
coming to you, sir?
Oh no, voice is breaking. Your voice is breaking.
Yeah. Yeah. His research includes radical number theory, circle method, L functions, subconvexity bounds, Riemann zeta function. Now it is fine, sir. Yes, you are. My voice is audible, sir.
It is audible, but lot of break in your voice. Lot of disturbance. But anyway,
Yes, I am trying to manage. Dr. Saurabh's research experience were as visiting scientist at HRI Allahabad, postdoctoral fellow, and DST Inspire Fellow at Indian Statistical Institute, Kolkata, and visiting scientist at University of Ulm, Germany. He has authored more than 24 research papers published and referred international. Yes, now, yes, sir. Ravinder, sir. Yes, sir. My voice is coming.
अनिल ब्रेक हो रही है तुम्हारी वॉइस, या तो स्टार्ट सर को इनवाइट करके स्टार्ट करिए.
Okay. Now I am going to invite our respected guest speaker. He had delivered more than 14 expert lectures in several national, international conferences and workshops. Dr. Singh also has organized several workshops, national, international conferences. We take this opportunity to thank him and we welcome you again, sir. To start this session, now I invite our respected guest speaker, Dr. Singh, sir. We discuss of circle method and subconvexity problem. Dr. Saurabh sir, over to you. Saurabh sir, over to you.
Okay, thank you, Anilji, for such a nice introduction. I think there is some problem with my Zoom application. So
Yeah, there was also some problem from my network. So sorry, not for complete introduction, but sir, you continue, sir. Thank you.
no problem, sir. No problem, Anilji. So it was very nice introduction. So I will talk about the work of Ramanujan. So it started with Hardy about the circle method. So I will come to the statement and all these things later. So there is problem with my Zoom, so I will not able to see the chats now. So if anything, please ask. Please stop me and ask your questions. So my talk has two parts. Part one, we will talk about what is called the circle method and how it become an important tool in analytic number theory. And second part, we will talk about the subconnectivity problem. Okay, to talk about the circle method, so there is a joint work of S. Ramanujan with G.H. Hardy, entitled asymptotic formula in combinatory analysis. It appears, it was communicated on 14th December 1916 and it was got accepted on 28th February 1917. Here in this paper he introduced the circle method. So it was said that by the Bruce one that in this very important paper Hardy and Ramanujan introduced what is now called the circle method. We will come later detail about what is circle method or Hardy-Littlewood circle method. It has since become the most important tool in analytic number theory. So we will see what is the circle method. So it was started with the study of the partition function. Partition function is how you can write given a natural number n, how you can write as sum of positive numbers. Like you can write 3 as 1 plus 1 plus 1, or you can write 3 as 1 plus 2, and general thing is 3 plus 0. So 3 you can write in 3 many ways. So hence P3 is 3. For 4 you can write is 1 plus 1 plus 1 and 1 plus 1 plus 2, 2 plus 2, 1 plus 3 and 4. So you can write in 5 many ways. Hence P4 is 5. Similarly, for if you compute for 6, you will get P6 is 11. This was only for the small values of n. So people are interested how this function Pn grows as n tends to infinity. So if you compute P10, it is like 42. P50, it already 204226. P100 is very large, and even P200 is 397299902938. So people want to study the growth of this function. So suppose you have a function f from a natural number to something, you want to study its growth, how it grows as n tending to infinity. So Kane Ono remarked that this was considered an impenetrable problem at that time because there was very little methods and tools were known to that time. So it was considered to be a very hard problem around that time. So, then there come the genius of the Hardy and Ramanujan. They proved that if you take the function Wn, which is of the size 1 by 4n square root 3, exponential of pi square root of 2n by 3, then you can approximate this partition function Pn by this Wn. As you can see, for n equal to 10, if exact value of Pn is 42, and the value of Wn is 48.1. If you look at the ratio of Wn by Pn, it is around 1.145. For n equal to 20, exact value is 627 and exact value of Wn is 692.4. And if you look at the ratio, it is converging to 1. And if you look at the P200, the exact value of Pn is 39722999029388, and the value of the function given by Hardy and Ramanujan is it's matching up to the integral part, only differs with the rational part. Because the Wn, it is an irrational number, involves square root and all these things, and Pn is an integer, so you can give only an approximation. But if you look at the ratio of Pn, Wn with Pn at n equal to 200, it is very near to 1. It matches up to the 6 digit of decimals. Okay. So it was pointed out by Silver, the circle method and its origins in the Ramanujan first letter. So it was trying to work with Hardy, but Silver pointed out that the circle method has its origin in the very first paper of Ramanujan, which he wrote to Hardy on January 11th, 1993 from India. So in that paper, Ramanujan wrote that if you compute the coefficient of the series, so if you look at the series, forget about the convergence and all these things. If you look at the coefficient of q to the power n in the series, 1 minus 2q plus 2q to the power 4 minus 2q to the power 9 and so on, and take its inverse. And if you compute the coefficient of q to the power n, it is the greatest integer or the least integer nearest to the expression 1 by 4n, 4 pi cos hyperbolic of 4 square root n minus sine hyperbolic of pi square root n by pi square root of n. So once the paper of Hardy and Ramanujan was published, then many people worked on him, and after the 20 years, that Rademacher gave the formula for Pn in terms of infinite convergence series, where ak are some constant, some exponential sums, which you don't have to worry about, and d by dn are some sine hyperbolic things. Yes. So this was the paper which I am mentioning. If you look at the point number 7, go to the 7th, go to the next page. This is the elaboration of the point number 7. Ramanujan, this is the writing of Ramanujan. He noted that coefficient of x to the power n in the expression of this one is nearest integer to this one. So G.H. Hardy remarked that there is always more in one of the Ramanujan formula than meets the eye. So you can see that if next, go to the next paper. If you go to the next page. Yeah, notice that if you take k equal to 1 in the expression of Rademacher, infinite expression of Rademacher, then the leading term, which correspond to the k equal to 1, this is resembles with the formula which Hardy and Ramanujan gives. So it has the expression for Pn was already somehow written hidden in the paper of first paper of Ramanujan. But also Silver wrote that in summer of 1937, so the great Silver, Ethel Silver, I had actually myself been studying the paper by Hardy and Ramanujan and had arrived at the Rademacher formula. So Silver independently proved the Rademacher formula, and he continued that it always seems strange to me that Hardy and Ramanujan did not end up with this formula. He was expecting that Hardy and Ramanujan itself, they might have itself proved the formula for the full infinite series. And I believe firmly that the responsibility for this rests with the Hardy. And he was believing that Hardy should have pushed the Ramanujan to give the complete formula. Okay, let us talk about a little bit idea how the Ramanujan work with this formula, how they obtain this formula. So look at the generating function, the partition function, which is 1 plus summation n from 1 to infinity Pn x to the power n. You can write this one as a reciprocal of product of 1 minus x, 1 minus x square, 1 minus x cube, and so on. Because if you take the right hand side and expand this one in the like a geometric series, so 1 upon 1 minus y, you can write as 1 plus y square, and so on. So here you will be getting for 1 minus x, power of x will be 1 plus x square, and so on. And for the power of x square, you will be getting x square, x to the power 4, and so on. And if you look at the coefficient of x to the power n for the right hand side, it is nothing but number of solution of k1 plus 2k2 plus 3k3 plus some rkr to be equal to n. And this is nothing but the Pn. So this is the informal proof, but you can look at some books, they have given the proof for this formula. So f of x is given by the reciprocals of the infinite product. Now if you change the variable z going to e to the power 2 pi I z, where z is in the upper half planes, means z is equal to x plus y and y is positive, then there is some called eta functions. Then you can write 1 by fx and taking the power of x to the power 1 by 24, this will be the neta z. Where neta is the modular function, you don't have to worry about what is called modular functions. They satisfy some property, then neta of 1 by z will be square root of z by I. So there you have to make some sense of square root. You have to take some branch of logarithm, and this is the branch of logarithm which takes value from 0 to 2 pi or minus pi to pi and eta of g. So you can relate reciprocal of minus 1 by z with eta z. And now if you apply the Cauchy theorem, if you have studied a little bit the complex analysis, then you can write Pn as 1 by 2 pi I integral over circle f of x by x to the power n plus 1 dx. So here gamma is the circle which has center at the origin and radius is strictly less than 1 for the convergence purposes. So that's why the name circle method comes later. So start with the expression of Pn, which is integration around a circle. Okay. But yeah, if you look at the function, if you read about the complex analysis, if you look at the function fx closely, so it has singularity near x equal to 1, and so x where the solution of x minus 1 to be 0, and more generally where solution x to the power n equal to 0. So the main contribution for these integrals come from the what are called the pole of the function, which is the rational roots of e to the power 2 pi I p by q. So main contribution comes from point 1. Let's go to next page. Yes, main contribution comes from the this is point 1 and all the rational roots of unity. Rational roots of unity means we are talking about e to the power 2 pi I p by q. Yeah. So, but there are infinitely many poles of the function. So you want to handle the integral. So what are the methods? Ramanujan gave the two ideas. One can either you can deform the contour, you can take the different path, or you can approximate the function itself. Go to the next point. Yeah, you can approximate the function itself near the similarity of the function, because as example, if you take f of x near the point 1, 1 is the heaviest, so you can approximate f of x by exponential of pi square divided by 6 1 minus x. And if you take the other roots, which is e to the power 2 pi I p by q, then you can approximate f of x by this function. Okay. So this is was the starting point for the circle method. But Ramanujan, he has many formula and all these things. Though our talk we will mainly focus about the partition function. But Ramanujan died around 26 April 1920. But after his death, his collaborators Littlewood and Hardy, they continued to work on this method. So between 1920 to 1928, Hardy and Littlewood, they wrote series of 8 papers with the same title, Some Problems of Partition Theorem, where they developed the method of Ramanujan. So we will get back to the other work of Hardy and Littlewood, but we will continue with the circle method. So, and its recent development. Okay, go to the next page. So Hardy-Littlewood put the circle method on a proper footing. So they give the proper explanation for this integrals. They approximate it, and they introduce some key concepts like major arcs, minor arcs, singular series, and singular integrals. And they also realize, which is the main point, that automorphy of the function is not needed. Means automorphy means you are relating function at which value -1 by z with z. And this is the main realization that automorphy of this function is not necessary for the method to work. That's why later part this is called the Hardy-Littlewood method, not Ramanujan and Hardy method. Yes. What are the general setup? So, and now we work in the general. So this is all about the partition functions where you are writing as n is equal to sum of two things, but you can take the general weights am. So let A, capital A, which is am, with the increasing sequence of non-negative integers, not necessarily your positive integers. You can take any integers, and you construct the series f of z, which is summation m from 1 to infinity z to the power am. Now, if you look at the f of z to the power r, so you can write as r many products, and coefficient and power of z will be z to the power am1 plus am2 plus amr. Now write this one, this summation as n, and then you are counting how many ways you can write n as sum of am1 plus amr. Denote this number as rrn. So f of z to the power r is nothing but summation n from 0 to infinity rrn z to the power n. And here rn is the number of representation of n as sum of r members of A. So now the famous Cauchy integral formula, you can write coefficient as the integration of generating function with some power. So you can write rrn is generating function is f of z to the power r divided by z to the power n plus 1 dz. And it's known that function f of z to the power has peaks, means they have singularity when z is near to the some rational number e to the power 2 pi I p by q, which q is small, denominator is small, then main contribution comes from the small denominators. The point the peaks from major arcs. Now you can take the interval around these points p by q on the unit circle. Interval is small enough. The main contribution comes from these intervals, and they constitute what are called the major arcs. And the rest of the intervals, the complement of the major arc is called minor arc. Also, you can avoid using the Cauchy theorem by approximating the function f of n. So f of z was this full series n from 1 to infinity z to the power am. But since you want to study from finite many n, so you can just approximate for suitable capital N. So you write f of nz is summation m less than n z to the power am. Now there is no convergence issue because this is a finite sum. Now you can take z to the e to the power 2 pi ix. So you write f of z to the power r. The first finite part at rrn, and the rest one is what are called the error term, crn z to the power n. Now here you can use the Fourier analysis, because this one is just nothing but finite sum. The rrn is. Then you can write rrn as integral 0 to n f of n. Now z is replaced by e to the power 2 pi ix. So f of n at e to the power 2 pi x to the power r with e to the power minus 2 pi I nx dx. Yeah. Now, what are the example of the methods of the circle method? Now, so given any positive integer k, let ak be the kth power of the integers. So 0, 0 power k, just 0, 1, 2 power k, 3 power k, and 4 power k. Instead of general ams, you are looking at the kth power of integers. Then just notice rrn is the number of ways writing n as sum of at most r many kth power. So rrn is number of writing n as am1 plus am2 and so on. So here for particular, this is the kth power. And it is known, it is proved by Hilbert also, that every natural number n can be written as sum of 4 squares, as sum of 9 cubes, and sum of 16 fourth power, and so on. Means if one put in the compact form, then if you want to write n, you can write Rn is to be bigger than 0 for every integer n. So let us give some definition. Define gk to be the smallest integer or such that all sufficiently large integer is at most r many kth power. So it is a theorem of Lagrange that you can write every integer as sum of 4 squares. So in general, we are talking about its kth power, and we are defining gk to be the smallest integer r. You can such that you can write every integer n as some power a1 to the power k plus a2 to the power k plus ar to the power k. And small gk, next please, next point please. Yeah. And define small gk to be, and small gk with the smallest r such that all integers. For capital gk, you are asking about sufficiently large integers, but for small gk, you are asking about all integers can be written as sum of the kth power. Note that capital gk will be always less than small gk. Okay, the application of the Hardy and Littlewood circle method, this shows that gk is less than k times k minus 2 times 2 to the power k minus 1 plus 5. For small value, this is true for everything, for every integer, but for small value, g2 is 4, as we have theorem of the Lagrange around 1776, that every integer can be written as sum of 4 many squares. And g3 lies between 4 and 7. G4 it proved to be 16 by Davenport, and G5 lies between 6 and 17. And as long for G2 small G2 goes, G2 is 4, the G3 is 9, G6 is 73. This is the remarkable work of another great Indian mathematician, Pillai. G5 is 37, but the hardest part was G4, which is proved by Balu, Dress and Desolé in 1986. Our Balchandra Ramasubramanian. Okay. After this work of Hardy and Littlewood, many mathematicians have worked on the circle method, and they have refined the methods, because there are many little tools known around the time of Hardy and Littlewood, and many things have been developed after that. So many people have worked depending on their problem. They have defined the new ideas, and they have introduced a new key concept, and they have refined the work of circle method. Their names include Klusterman, Vinogradov, Roth, and Davenport. And in modern version, what is called Matthias-Zutila, Duke, Friedlander, and Ivanik, and Heath-From. Okay. So what are the other application of the circle method? Circle method and application to the Vinogradov are called ternary-Goldberg problem. It says that every sufficiently large odd number is sum of 3 primes. Using circle method, Vinogradov has proved that every sufficiently large odd number is sum of 3 primes. And it has application to the Roth theorem. What is Roth theorem? That any subset of integer 1 up to n contains at least Cn by log n elements. If you take this one, it has 3-point arithmetic progressions. If you take any subset of 1 to n which has at least some constant times n by log n many points, then it will have at least one 3-point arithmetic progression. Means it will have points such that a plus d, and a plus 2d. Means any subset of 1 to n which has this many points will have points like a plus d, and a plus 2d. And also it has application to the Davenport-Hillbroom, which is approximation of a rational number. So if you take the kth power, and if you look at the coefficients which are not necessarily integers, they are real numbers. Then you can approximate, you can go to near to the 0, you can approximate 0. So you can take lambda to the power x1 plus lambda 2 to the power xk plus lambda r to the power xr. You can take the moduli, and this will be less than neta for any neta bigger than 0. And this is the application of Burst theorem. This is about the counting the rational points on some varieties. You don't know, but okay. Now we will talk about what is the relation between the circle method and delta symbols. So recall the truncated series f(x) is given by e to the power 2 pi I xkm, where m varies from 1 to n. Okay, and let CR be the nth Fourier coefficient of f of n to the power r. By definition, CR is nothing but RRn for n less than equal to n. Then recall integration 0 to n e to the power 2 pi I xn. E of xn means e to the power 2 pi ix. If you integrate this one, you will obtain 0 if n is not equal to 0, and this is 1 if n is equal to 0. That's give the expression for delta n. Now write CRn as sum of series summation m CRm delta mn, because if m is not equal to n, you will get 0, and if m is equal to n, you will get CRn. Now expand this delta symbol using the integral 0 to 1 e of x m minus n, and this is nothing but just plugging the coefficient. This will be nothing but f of n x to the power r e of minus xn dx. Just CRm e of xm will be nothing but f of n x to the power r. Okay. Now, if you can expand this delta symbol nicely, then any nice expression of delta symbol, that is called the circle method. So if you can expand delta n, then with some nice explanation, then you can see that you will get some formula for CRN. So many mathematicians work for the expansion of delta symbols. So in circle method, in vague sense, you can say as some nice expansion of delta symbol, delta n. So right, so like Klustermans has expanded like delta n to be 2 real integration 0 to 1 summation over q, summation over a, which has co-prime with q, 1 by aq e of a bar n by q minus nx by aq dx. If we substitute the expression for delta n in the previous equation, we obtain the value of CRn as the last line. Yes. And Jutila has expanded the circle method in the following sense. So he has approximated the a by q, the rational point with small denominators a by q with some delta, and he obtained the following expression for the delta symbols. So here there is comes with main term plus there is some error term which you can control. Yes. Yes. Now Duke, Friedlander and Ivani, they developed a circle method completely independent of the previous case. So the thing you want to detect n equal to 0. Delta symbol is nothing but you want to detect n equal to 0. You want to give value when n equal to 0. It is 1. When n is not equal to 0, you want to give value as 0. So they use that an integer is 0 if and only if it is divisible by for every integer. So n equal to 0 if and only if d divides n for every integer n. Using the divisibility criteria, they can detect the integer and they obtain the following expression for delta n with cost of some weight function GQX. But remarkable thing is that it's not very clear for that first glance, but they are able to free the arithmetic variable a from analytic variable. So note that there is no A involved with X, but in the Kloosterman circle, A involved with X. So integrals which are continuous variables, they are called analytic variables, and which are discrete variables like A and Q, they are called arithmetical variables. In many applications, if there is a relation, if there is some interchange between arithmetic and continuous variable, then there are some problems. But yeah, in this circle method of Duke, Ferdinand, and Ivanich, A and X are separately completed. Okay. Now, what are the modern ones here? So, note that all the previous expansion of delta n, they are based on the harmonics of e to the power 2 pi x. E to the power 2 pi x, they are points on the unit circle. People can ask, there are any other versions of the circles where you can detect delta symbol with some other variables? There is something called trace formula, trace, one of them is Peterson trace formula, trace formula for GL2 and 3 on. Point is that there you can also have the formula for delta n using not only the arithmetic harmonics like e to the power 2 pi I, but there are some other harmonics coming from the modular forms. Okay. Now we come to our second part, what is called the subconnexity problem. In vague sense, subconnexity problem, we will study the growth of certain functions. Like we are studying the growth of Pn. Here we will study the growth of certain function, f of s, which is an analytic function, but only at the central line. We will come back what is called central line. So we want to study the growth of f of half plus it as t tends to infinity. That is called the convexity problems. So convexity problem has originates with a Riemann zeta function. If you define the Riemann zeta function, zeta s is summation 1 by n to the power s. This is absolutely and uniformly convergent series, and real part of s is bigger than 1. And in that region, you can give the infinite product 1 minus 1 by p to the power s whole inverse. These two are equivalent to that every integer can be written as sum of the primes in unique, product of the primes in unique way. Then this one you can meromorphically continue to the whole complex plane. Earlier it is defined only for sigma bigger than 1, but you can make a sense for whole complex plane having a simple pole only at s equal to 1, and it has some nice functional equation also. So if you multiply the zeta s with gamma function and take some suitable power of pi, then you can expand, you can write in terms of the integrals 0 to infinity x to the power s by 2 psi of x dx, where psi x is nice theta function, and from 1 to infinity e to minus pi n square x. Now there is something called the Poisson summation formula, which relates value of f summation f of n with summation f of hat n, where f hat is the Fourier transform of f. If you use this Poisson summation formula, then you will get a relation of similar kind where you are getting the relation of eta function. So you can write 2 times psi x plus 1 will be equal to 1 by square root of x, 2 of psi of 1 by x plus 1. So there is an expression which relates psi of 1 by x with psi of x. This expression is useful for the analytic contribution of the Riemann zeta function, and you can prove that using, you can truncate this 0 to 1 and 1 to infinity. For 0 to 1, apply this relation from psi of 1 by x. Then you can write left hand side as with pole s into s minus 1 and following expressions. And note that the integral previous one, note that go to the previous slide. Note that the right hand side is symmetric about s with 1 minus s. If you replace s with 1 minus s, then right hand side is unchanged. Hence, the left hand side is also unchanged. So you get what are called the functional equation, which relates the value of s with 1 minus s. Yeah, go to the next please. this is the Riemann zeta function. Earlier you defined for the real part of S bigger than 1. Now with the functional equation you can make sense for real part of S which is strictly less than 0. The only mysterious thing lies between 0 to 1. This is called the critical strip, and the line which is in between of the critical strip, like sigma equal to half, this is called the critical line. So there are some zeros of Riemann zeta function for the negative even integers like -2, -4, -6 and so on. They are called the trivial zeros. And it has proved that Riemann zeta function has infinitely many zeros in this critical strip. And what is the Riemann hypothesis? Riemann hypothesis says that all the non-trivial zero has to be lies only on the line. There are no non-trivial zero except for this line. So it says that the zero which is depicted here cannot exist. Okay. Okay. So if for sigma bigger than 1, you can know the growth of the Riemann zeta function, and you can apply the functional equation for sigma less than 0. You know the growth of the zeta function. Only mysterious thing is lie about the line critical strip 0 to 1. But if you know this growth at half, then you can apply some principles. So you can know the growth in the whole entire critical strip. Yeah. So problem is to understand the size of zeta function inside the critical strip. So you can apply the fragment Lindelof principle. It is enough to study the growth of only on the critical line half. So using the functional equation and fragment Lindelof principle, you can get that Riemann zeta function at half plus it is bounded by t to the power 1 by 4 plus epsilon. So your function is growth is like t to the power 1 by 4 plus epsilon. But if you use the Riemann hypothesis, then consequence of Riemann hypothesis called Lindelof hypothesis, it says that the growth, the exponent 1 by 4 you can replace by the value 0. So zeta of half plus it is growing like t to the power epsilon. Okay, so what are the subconnexity problems? So you at one step you have the trivial bound called 1 by 4, but Riemann hypothesis, which is very big things, it is giving you that it is going like t to the power epsilon. So subconnexity problem is to improve the bound from 1 by 4 to 0. So if you can prove that zeta half plus it is bounded by t to the power 1 by 4 minus delta, then that's called the subconnexity bound. Okay, so this subconnexity problem, this one has origin in 1920. So like on Thursday, February 10th, 1921, there was a conference having 30 members, where J. Littlewood was one of the participants, and he communicated one paper with the conference, that research in the theory of Riemann zeta function, and he wrote that it would occupy too much space to give any detailed description of the method used in these research or any full statement of the previous work in the same subject, and I have confined myself in a main to bare statement of the result. And what was the result? Just he says that, next point. He says that zeta half plus it. So he says that in a paper written in collaboration with Professor G.H. Hardy, they have proved that zeta half plus it is growing like t to the power 1 by 6 plus epsilon. So from 1 by 4, they come to the 1 by 6. But curiously, this paper was never published. They don't care about the publication and so on. Go to next. So we state the following theorem. Stated that zeta half plus it is bounded by t to the power 1 by 6 plus epsilon. This is bound. Go to next. curiously, this paper of the Hardy and Littlewood was not published. Independently, Hermann Weyl has also proved that zeta half plus it is bounded by t to the power 1 by 6 plus epsilon. But while paper was also not published, then later it was written by the Landau. Okay, so the bound of Hardy-Littlewood is 1/3 down towards the Lindelof hypothesis, because if you break interval 0 to 1 by 4 into 3 parts, like 1 by 12 and other things, then you are 1/3 away from the 1 by 4. So what are the proof for the Weyl bound they have given? You can just approximate functional equation. So you can take the zeta half plus it. Earlier it was given by with infinite series, but in this critical strip, you can write with finite sum summation n going root t by 2 pi 1 by n to the power half plus it with chi, which is coming from the functional equation, n to the power half minus it, and there will be some error term because you are truncating from infinite series to some finite series. Now, if you estimate trivially the summation n going up to root t, 1 by root n, you will get t to the power 1 by 4. So you will get your bound, convexity bound, which is big O of t to the power 1 by 4. Now, point is that if you can show any cancellation of this summation n going to root 2 n to the power it. So 1 by n to the power half is Knight's function. You can differentiate and all these things. So you can take it out by applying Abel summation formula, something called Abel summation formula. So only thing, if you want to show some cancellation in n to the power it. So n to the power it, they are oscillating on the unit circle, and you expect there are lots of cancellations. Like if you add sum of nth roots of unity, you obtain 0. So main object is study the sum of the form summation n going up to root t n to the power it, and using this one you can write as e of t by 2 pi log n. Some of these top form, they are called exponential sums because this involve exponential of some complex things, and they have the other applications to other branch of mathematics also. And this is one of the central problem in analytic number theory. To get cancellation means trivial cancellation is number of billions. So E of ix, this is bounded by 1. Trivial estimate of this one is equal to the length of the interval. And problem in analytic number theory, to get some cancellations, you want to show this is whether it is less than some power of root t. Yeah, so this is the paper of the Weyl. There he introduced this study of exponential sum by introducing so-called the Weyl differentiation method. Just take absolute value square and write this one as k plus r minus kr. Is there any questions? Yeah. So this Lindelof bound 1 by 4 was proved in 1906, and then Hardy-Littlewood proved bound 1 by 1. Lindelof bound is 1 by 4. Hardy-Littlewood proved 1 by 6 in 1920. So you may think that given a magnificent progress of in mathematics in the last 100 years, you expect that much better bound. But unfortunately, the current record is, so from 1 by 4 to 1 by 6 is like 1 by 4 minus 1 by 12. So you can improve 1 by 12 in just 14 years. But in last 100 years, we are just able to improve t to the power 1 by 6 minus 1 by 84. It's very small in comparison to the Hardy and Littlewood. So there are 3 techniques to tackle the exponential sums. One is the Weyl differentiation introduced by the Weyl, Vanderkerput, and Vinogradov. So this is the history of the exponent. So 0.25 like t to the power 1 by 4. It is just a Lindelof principle and functional equations proved by Lindelof in 1908. Then Hardy-Littlewood, from 0.25 they go to the 0.1667 in one go, and from there you can see there is a little bit improved from 0.67 to 0.50 by Walpsis in 24, And then their third decimal improvement 0.47 by Titchmarsh, and then Phillips ranking, Koloznik, Mini, Bomberry, Huxley, and Bourgain, the latest one. He in first paper he improved 0.1550, and in second paper he introduced to the third, improve on the third decimal. He improved that 0.1548. You can just see that this is nothing but 1 by 6 minus 1 by 84. Okay. The people may ask, why do you care about the subconvexity? So I would like to tell one story. There is a friend, the Gerald and Hippo, they were a friend. Then he could not see his friend Gerald for several days. Then one day he is coming, so he is asking to Gerald, what happened to your trunk? This is the famous story by Mo Williams. Then Gerald told him, go to the next one. Yes, I broke my trunk. Then he asked, how did you break your trunk? How did you break your trunk? Then he said that, then I had an idea. I want to lift Hippo onto my trunk. Then Piggy asked, why you want to lift Hippo on your trunk? And Gerald replied, because I want to just I want to lift. So why you care about subconnectivity? Because I want to just study subconnectivity, but it is not like that. It has some very interesting applications also. Like Ingham shows that if you saw the bound of form zeta half plus it is bounded by t to the power c, then if you denote Pn to be nth prime, then gap between Pn plus 1 and Pn is given by the Pn power 1 by 4c divided by 2 plus 4c plus epsilon. So Pn is the size of the nth prime. So if in particular, if you take c to be 0, which is you take from m, c to be epsilon, which comes from the Lindelof hypothesis, then Pn plus 1 minus Pn is bounded by Pn to the power half plus epsilon. Why it is important? That legendary conjecture, it is not proved that there is always a prime between two consecutive squares. If you take two consecutive squares like 1, 4, 9, 16, 25, then there will be always a prime between n square and n plus 1 square. Okay. So this convexity problem we have introduced only for the Riemann zeta function, but it has also generalization to the other L functions. So what are the L functions? They are the LS pi. They are nothing but summation an by n to the power, summation of the form an by n to the power s. If you just take an to be 1 for every n, then you will get back to the Riemann zeta function. So general L functions, you can say vaguely in the sense that they are formed series of the form an by n to the power s with some additional conditions. What are the additional conditions? That they should have functional equation and they should have what are called the normal growth around 0.5 plus it, and they should have analytic continuation to the whole complex plane. So what are the other applications to the subconnectivity problem? Now consider this sphere x square plus y square plus z square to be n, where n is any positive integers, and let capital Rn to be the number of solutions for this equations, where x, y, z belongs to z cube and x square plus y square plus z square to be equal to n. Or number of number of integral solutions to these equations. Then Siegel's theorem, Siegel shows that if n is not of the form 4 to the power k 8l minus 1, then your Rn is at least n to the power half minus epsilon. Now, if you divide this equation x square plus y square plus z square to be equal to 1, just divide this equation by n, then you will get x by root n plus y by root n square plus z by root n square to be 1. Then Rn by root n, they will be light on the unit sphere x square plus y square plus z square to be equal to 1. Then you want to study the distribution of Rn by root n as n tends to infinity. Go to next. Yeah. So for if you take n to be 1, 0, n, then the plot Rn by root n on this sphere. So you are obtaining following points. For larger value of n, you will get many value of Rn's. As n tends to infinity, and using subconnectivity, one can show that the points on this sphere, they are equidistributed. Equidistributed in vague sense, you can say that if you take, yeah, just go to the next step. Equidistribution means is that if you take V in Rn, such that V by root n, this belongs to the unit sphere sigma, and you divide by the count of whole of Rn. If you take any sigma, which is subset of Sn, and if you want to count number of lattice points belong to that set, divided by the total number of lattice points. If you take limit n tends to infinity, then this will be nothing but integration over the sigma d mu. The d mu is the unique Lebesgue measure on unit sphere. Then subconnectivity problems implies the equidistribution. So if you prove the subconnectivity problem with some function L half f twisted by chi, then you get the equidistribution of the lattice point. Okay. There is some other application to the. We will not. Let's skip for this one. Go to next step. This one. Okay. So why we care about the subconnectivity? One of them is that there is one paper, famous paper of Peter Sarnoff and Enrique Manis, the perspective on the theory of analytical function, where they list some important problems in number theory. They state that main problem is the grand Riemann hypothesis. Riemann hypothesis is like we have said that only non-trivial zeros of Riemann zeta function lies on the line sigma equal to half. Then this you can generalize to the general L function. You can show that non-trivial zeros of L functions, for general L functions, they lies only on the line sigma equal to half. And so, and in there he stated that because of many applications, we single out the problem, which is basic one. So this proving Riemann hypothesis is the most difficult problem in the recent years. It has not, there is no progress at all. And he says that important problem is the subconnectivity problem, and half plus IT proving a bound of the form 1 by 4 minus delta. Okay. Okay, so we will discuss now the proof of Hardy and Littlewood, the Weyl, they were just using the consideration of exponential sums using the Weyl differential sum method. But now, since we have made a progress towards the circle method also, now we can give the proof of the Hardy bound using the circle method also. So think just if you take the square of Riemann zeta function, you will get dn by n to the power it. Now we want to separate dn with n to the power it. So you can write as dn and m to the power it detect n equal to m. When n is n equal to m, you will get s, and n is not equal to m, you will get 0. Now we have seen that circle method is any nice expression for this delta function. Apply the circle method, you will obtain the following expression for s. Now, using some well-known techniques called Poisson summation formula and all these things, go to the next step. Something called summation formula. So, use the summation formula for dn, summation formula for it, then evaluate some integrals. You will get back to the proof of the while bound, which is called 1 by 6. You will get the while bound, but with now the circle method using the method of Hardy and Ramanujan, started by the Hardy and Ramanujan. Yeah, this is the details. We will skip the details. Okay. Now, with this, we have come to the full circle. We are back to the Hardy Littlewood in 1920s. In one hand, they were developing the circle method, and on other hand, they were studying the bound for the Riemann zeta functions. Their proof the subconvective bound for the Riemann zeta function was not based on the circle method. Their proof was using the Weil differentiation technique. But now, after 100 years, we understand that the circle method is an effective tool and a very important tool to study the growth of the L function, not only the Riemann zeta function, but also to the general L functions. It can be used to prove the Weil bond without using the Weil differentiation techniques. So I myself given a two proof for the Weil bond, but they are not important for the stocks. Okay, I think I would like to stop. Thank you so much for your attention. If you have any questions, please feel to ask.
Dear
Anil sir,
participants, yeah.
I think
over,
there is no question in chat box. If
dear
anyone asks,
participants, if you have any question, you can write in the chat box. Chat box is enabled for everyone. Over to Chhatrapal sir.
yes, sir.
No, you can unmute them also. They can unmute and answer.
Anand. Anand.
यस सर
अनम्यूट कर दीजिए अगर शायद कोई डायरेक्टली पूछ सके क्योंकि यहाँ पर तो कोई क्वेश्चन नहीं दिया है
ठीक है ओके
Dear participant, please raise your hand so that we can unmute yours. No? I think no one has any question. But sir, I have a question. In starting slide, sir, you mentioned somewhere Pn and Wn. So Pn, I think, is the number of partitions. What is this Wn? And then further, please elaborate the ratio Pn and Wn.
Yeah, so Pn is the exact number of partition of
Partitions. Yes.
And Wn is the formula coming from the formula of the Ramanujan, where it says that you can approximate Pn by Wn. Wn is nothing but 1 by 4 square root of n e to the power 2 pi, something like that.
This is the fixed one.
Wn is the function and Pn is the exact value.
Okay. So, no questions. Good afternoon, everyone. On behalf of Department of Mathematics, RSD College, I send my very hearty gratitude to the speaker of this session, Dr. Saurabh Kumar Singh, Department of Mathematics and Statistics, IIT Kanpur. Sir, you enlightened to us with your knowledge and wisdom on the topic circle method and subconvexity problems on the occasion of 135th birth anniversary of great Indian mathematician Srinivas Ramanujan. Thank you so much, sir. We have you with us. Thank you so much, sir. Now over to Kapil sir for the next session.
कपिल सर अनम्यूट कर लीजिए.
Very good afternoon to all of you. Myself, Kapil Kumar, teacher in charge, Mathematics Department. On behalf of Mathematics Department, ARSD College, I welcome all the participants. So, as you all know, today is the birth anniversary of Srinivas Ramanujan, and his birth anniversary celebrated as National Mathematics Day in India. So, on his birth anniversary and on National Mathematics Day, every year our department organize many webinars or seminars and different talks on this occasion. So this year also we organize a talk which is Ramanujan, the Great Indian Mathematics. So one guest speaker already discussed about their subject. Now it's time to introduce the second guest speaker. So it's my immense pleasure to introduce our guest speaker, Dr. Mahendra Kumar Verma, for the second session. Dr. Mahendra Kumar Verma, currently working as an assistant professor in the Department of Mathematics, Indian Institute of Technology, Roorkee. He received his PhD degree. This is entitled on symplectic periods for inner forms of GLN advisors under the supervision of Professor Ravi Raghunathan and Professor Deependra Prasad from Department of Mathematics, Indian Institute of Technology, Bombay. His area of interest is automorphic forms, harmonic analysis on periodic groups, representation theory of periodic groups. He has more than 10 years teaching and research experience. Dr. Verma worked as a scientist B in DRDO. He also postdoctoral fellow in Ben Georgian University of Negev, Israel. He is also postdoctoral fellow, Harish Chandra Research Institute, Allahabad, and he also worked as an assistant professor in IIT Jammu. He has authored more than 6 research papers published in various reputed international journals. He also delivered several experts guest lecture in workshop, seminar, and conferences. So once again, I welcome Mahendra sir, and over to you. Thank you.
Yeah, thank you, Kapilji, for your nice introduction. And thanks to department and even college for invitation in this program. Yeah, so I will start, but before that, I request to admin that please allow me to share. I have joined via another login, another Mahendra Verma. So can you allow me to share through that one? I mean, you have to make co-host using that another Mahendra Verma. I have logged in by one ID.
Yeah.
Please allow me.
Anil sir, first make sir's name as a co-host, and then sir will be.
सर कर दिया हमने. हेलो. हाँ सर, मैंने कर दिया है.
हाँ हाँ ठीक है कर दिया. हाँ हो जाएगा अभी. So actually, I have not made a slide. This is handwritten slide, and I hope that this will be accessible for all the students also. But at any, can you hear me? Can you confirm I'm audible?
Yes, sir. Yes, sir. You are audible.
Yeah. So just, I mean, this is talk for mainly for the students and even for everyone, but mainly for the students. So if any student has any questions, they can ask in between or at the later point. So let me start. So this title of the talk is Ramanujan tau functions. So first I will say about something about the Ramanujan, and this talk is not too much, I mean, elementary in nature, and this involves some old mathematics, maybe 200 years ago, and some combination of recent mathematics, but only overview, not any technical detail. And there is some intersection with Professor Saurabh Singh's talk also. Yeah, so it will be easy for me. So there is some story about the Ramanujan. You can say that, yeah, so some life is introduction about him. So Srinivas Iyengar Ramanujan was born in the year 1887 on December 22nd. That's why we are celebrating his birth anniversary today. And we know also Government of India declared this as a National Mathematics Day also. So, and he was more or less, I mean, he was self-taught and become a universal genius with his fundamental contribution to the number theory. So in college days, I mean, he in 1903, at the age of 15, he was admitted to government college in Kumbakoram. So this is some place in Tamil Nadu. But he failed his exam because he spent, means he failed in other courses because he is spending too much time in mathematics only. So having failed to earn a college degree, Ramanujan accepted a job in the port trust office as a clerk. So at that time, there are two mathematicians at that time. One I remember, like this mathematicians S. Iyer suggested. Ramanujan at that in South India, this mathematician S. Iyer, Ramanujan is learning a lot from this S. Iyer, and he suggested Ramanujan to write to G.H. Hardy. He was a mathematician at that time in England. So Ramanujan wrote to G.H. Hardy and his, I mean, that famous letter on 16 January 1913, in which he listed theorems. I mean, he introduced himself in the first page, and you can say in letter only theorems and various formula. And it is difficult to understand. So for Hardy, even it is difficult to understand his work, what he wrote, these theorems and formula. So he looked his paper, and even he invited his colleague, this Littlewood. Already he mentioned his name, Dr. Saurabh already mentioned. So Hardy and his colleague Littlewood looked in his paper, and then they said that this work can be done only by a genius. So this work of genius Ramanujan. So from 1914, so now in 1914, I think this Ramanujan left for England, and he and Hardy worked there. They had some fruitful collaboration, and during that time, this Ramanujan wrote near about 30 papers, and some jointly with Hardy. So this is about his some brief introduction about his life. Now we will do some elementary mathematics. For that, I need some definitions. This is very basic definitions. I mean, you don't have to know any kind of mathematics, but yeah. So this N denotes natural number and C denotes set of complex numbers. And any functions from this set of natural number to complex number are called arithmetic functions. Means domain is the natural number and range is the complex number. And this multiplicative functions are called arithmetic functions if those functions satisfy this kind of property, that fmn times fm into fn whenever m and n are co-prime. So like so like if you are taking m and n 2, 3, then this should be equal to, so f6 is equal to f2 times f3. This kind of functions are called this kind of arithmetic functions are called multiplicative functions. And one can see here examples. Like you take this sigma functions. You might have seen this in your elementary number theory course. Otherwise, it is here. So this sigma function, this is sum of divisors. So means if you are calculating sigma of n, you take all the divisors. So this k, this vertical lines means k divides n. So you take sum of all divisors. Like for sigma 15, divisors are 1, 3, 5, 15. So this is 24. And this is a multiplicative functions. Means if you know value at the prime, then you can calculate value at for every one. Like sigma 15, it is easy to calculate. This sigma 15 is sigma 3 times sigma 5, because this is a arithmetic function, multiplicative functions. So, and another example, you can take this Euler 5 functions that you also have seen at some point. This is the number of integers, number of positive integers, you can say less than or equal to n and relatively prime to n. So here 515 is 8. So these are two examples. There are many arithmetic functions. We will see one here. And yeah, so another theorem, I mean, another notion, you know, this fundamental theorem of arithmetics that says that any natural number greater 1 can be written as a product of distinct prime powers. That everyone knows, but this is one of the important, this is one of the basic theorem in number theory in algebra, that any integer greater 1 can be written as a prime powers, prime of distinct prime powers. And using that, you can say that the sigma of phi can be written as sigma n is equal to sigma p1 raised to the power kn, sigma pr raised to the power kr. So if you want to know value of this multiplicative function for any natural number n, it is sufficient to know the value at the prime power. So let's introduce another, this Riemann zeta function. Already in our previous talk, you have seen this in a great detail, but let me write it here, this zeta s. So s is the complex number first. S is the complex number, and this is summations varies over n to infinity 1 upon n2 raised to the power s. If you expand this, this is like 1 plus 1 upon 2 raised to the power s plus 1 upon 3 raised to the power s plus dot dot dot. But any question? Yeah, but this, you know, this series makes sense only for real part of s greater 1. That is the meaning, that in other terms, this series converges only for real part of s greater 1, because if you put s equal to 1, then this is a divergent series. So this series makes sense only for real part of s greater 1. This is called Riemann zeta functions. And let's see some values, some special, like n equal to 1. If you take n equal to 1, you will get sigma 1 by n. This is 1 plus 1 by 2 plus 1 by 3. This is a divergent series. You will get value infinity. If you take s equal to 2, so this is, you can say zeta 1, this is zeta 2, means s equal to 2. Sigma summation 1 upon n square. This is pi square by 6. You might have seen proof at some point, but zeta 3 is, yeah, this is 1 upon n cube, and then 1 upon n4, summation 1 upon n4, that is pi raised to the power 4 upon 90. But why this is connected with Ramanujan? Let's see. So you know, if you write this zeta minus 1, what you will get? If you write s equal to minus 1 in this s equal to, if you write s equal to minus 1, then you know you will get 1 plus 2 plus 3 plus 4 plus 5 and all these things, which is here. I have written here zeta minus 1. But somehow this Ramanujan calculated that this is minus 1 by 12. Of course, this is a divergent series. This is a divergent series. So there is no, you cannot assign any value. I mean, this is infinite one. You cannot sum this one. But Ramanujan, I mean, by his own method, he has calculated zeta minus 1 is equal to minus 1 by 12. And this I can explain by using analytic continuation that already, I mean, in previous talk you have listened. But before that, before going back to this, why this can have a meaning, I can give you one example. Like if you want to, suppose you have this series 1 minus 1, I hope you have seen, otherwise you can see it here, 1 minus 1 plus 1 minus 1 plus 1 minus 1. This is dot dot dot. You know, this series, this infinite series, you know, this is a divergent series. This is a divergent series. Everyone knows this. And if you write in this form, 1 minus 1 plus 1 minus 1, if you group in this form, 1 minus 1, then this will become 0. And if you write same thing in this form, 1 minus 1 plus 1, yeah, sorry, you can write this also in this form, minus 1 plus 1. If you can group in this form, then this will become 1. Of course, this is a divergent series, but you know this S is equal to half. This has some, I mean, you can assign, I mean, someone has assigned, I forgot who did this, you know, this you can give the meaning, and you can give the, you can assign this value half. Anyone knows this proof? Let me write it here. This is very elementary, I mean, way to see this. So if so, I want to say that this S equal to, of course, S is divergent, but I can give a meaning S equal to half. I want to convey you that this is a divergent series, but Ramanujan gave this the meaning that this is minus 1 by 12. Okay, so I can write this. You know, if you write this 1 minus S, what is this? 1 minus S. 1 minus S is again, you know, S is this. So 1 minus S is again 1 minus 1 plus 1 minus 1 plus 1 minus 1. Dot, 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 dot. Again, this is S, correct? 1 minus S is again S. So you can say here 2S is equal to 1. So you can say that S is equal to half. So there is a way to assign this summation, some divergent series, some value. So similarly here Ramanujan gave this, I mean, very zeta minus 1, this assign his value minus 1 by 12, but this can be explained using analytic continuation. So in previous talk you have seen functional equation for zeta S. So this zeta S, what I have defined as an infinite sum that makes sense only for real part of S greater 1. Means only real part of S greater 1 means only this part, this is defined. Only this part, this is defined. But if you have any, so what is analytic continuation in layman language? If you have any function defined on some domain, if you have some analytic function defined on some domain, you can extend its domain. So you can extend its domain, whole complex plane. You will get, so there exists a new function which is analytic on whole domain, but if you restrict to this part, then that will become our zeta S. So that is the meaning of, you can say, simple meaning of analytic continuation. So if you redefine this, then zeta can be defined over whole complex plane, and from here you can give the value, like here if you put, suppose if you put zeta 2, if you put here zeta 2, so here you will get zeta minus 1. So here, and already we know zeta 2 is equal to pi square by 6. So you can calculate zeta of minus 1. So it is easy to find out the value of zeta, I mean, using analytic continuation, but one needs a complex and knowledge of complex analysis. But that, I think that time it may not be available to Ramanujan. So, yeah, and then you can talk about this trivial zero of zeta S. Once this zeta is defined in whole complex plane using analytic continuation, you can talk about trivial zeros. Trivial zero means S equal to minus 2, which is on this real line, because you can see here, if you put here S equal to minus 2, minus 4, minus 6, this will become 0. Zeta S will become 0, but this is called trivial zero. And non-trivial zero, non-trivial zero lies between, in this critical strip, you know, this vertical strip, you can see this 0 to 1, this vertical strip on this. So this is called critical strip in between 0 to 1, and one knows that this all non-trivial zero lies on this critical strip, but Riemann hypothesis says that all non-trivial zeros are on the critical line, this line only, real part is equal to half. This is the Riemann hypothesis. One knows that this all zeros lies on this strip, but Riemann hypothesis says that all non-trivial zeros are on this critical line. Yeah, so this is Riemann zeta function came because because of this Ramanujan divergent sum came here. Now I introduce something called Euler's identity because this is also related with zeta functions. So zeta, this one knows this zeta is as infinite sum, but this can be written as a infinite product. So infinite sums over is all natural number, but infinite product is over only primes. And here you can use this fundamental theorem of arithmetic that any natural number can be written as a product of prime powers. So zeta s can be written as this product of infinite product of this. And so infinite sum you can see as the infinite product also. This is given by Euler's. And then using that you can prove, one knows that this Euclid theorem that there is an infinite number of primes. Infinite number of primes. There are many proofs for infinitely many primes, but using this you can see there are infinitely many primes because this infinite sum can be written as infinite prime. And for if you think s equal to 1, for s equal to 1, this series diverges, left hand side diverges. And here you can see if there are only finitely many primes, then this is a finite product, you will get a finite number. So this means you cannot have only finitely many primes because this left hand side is always infinite, and right hand side, if there are only finitely many primes, then that is a finite. So you can say there are infinitely many primes. Now consider another things called Euler functions. This is some, you can think as an infinite series in X. So consider infinite product phi x, which is product of 1 minus x raised to the power n equal to 1 to infinity. So like 1 minus x square, 1 minus x cube. And try to expand this, try to write down few terms. If you write few terms, then you will get 1 minus x raised to the power 1 minus x square plus x raised to the power 5 plus x raised to the power 7 and dot dot dot. And what is the significance here? These powers, this like here, you see the powers where sign changes. You see the powers where sign changes. So first sign here is this -1, and here power is 1, and then here next sign changes is here plus. So here is 5. So I am writing here 1, 5, and next sign changes is 12. So here I am writing 12, and next sign changes is here plus minus 22. So if this sign changes 1, 5, 12, 22, 35, these are a special number. These are called pentagonal numbers. And there is general formula for this. If you write n equal to 1, you will get 1. If you write n equal to 2 in this one, you will get 5, and all these things. These are called pentagonal number because you can see here n equal to 1. This is only 1 point, but if you write n equal to 5, this you will get a pentagon. Yeah, there are 5. And similarly, if you take 12, you will get another bigger pentagon, and so on. So that's why these are called pentagonal numbers. So here I took phi x and its power 1, you can say, but Gauss took power 3. If you take this power 3 here, phi x and then power 3. So here 1 minus x, 1 minus x square, 1 minus x cube, this is infinite product, but you have to take power 3. And if you try to expand, write few terms, you will get 1 minus 3 raised to the power x1 plus 5x raised to the power cube minus 7x raised to the power 6 plus 9x raised to the power 10. And here you see the coefficient. Coefficients are 1, 3, 5. Sorry, here again you see these powers. All the powers you see 1, 3, 6, 10. These are the powers. So these are called triangular numbers. Why these are called triangular numbers? You can see these are because they represent point on the triangle. If you see this is, if you see only this is 1, if you see this is a triangle, so there are three, 1, 2, 3, correct? And if you count one more thing, this is also a triangle, but now this is 6 and 10 similarly. Yeah, so this is called triangular number. This is given by Gauss, pi x raised to the power cube. This, if you can write in this form. So this n square plus n by 2. This you can see in any elementary number theory book. This you will get this n square plus n by 2. And yeah, so this is triangular number. But you see, this, if you, this is by Ramanujan, if you take 24th power of this infinite product, so phi x is an infinite product, and you take again 24th power and expand this, you will get this few, try to expand few terms. So you will get this 1 minus 24x plus 252x square minus 1472x cube plus plus 4830x raised to the power 4 plus dot dot dot. Let me write this as a summation n equal to 1 raised to the power 30, and I will write this coefficient by tau n, x raised to the power n minus 1. Means if you take n equal to 1, this is the coefficient of, this is, you will get constant. You will get, and if you take n equal to 2, you will get this tau 2, correct? So this is called Ramanujan tau function. This tau of n, these coefficients are important here. This is called Ramanujan tau functions, and here you can see tau is a function from natural number to complex number. We will come in a great detail now. So yeah, now Ramanujan tau functions. So in 1916, Ramanujan introduced a function which is called Ramanujan tau functions. And tau is an arithmetic function defined as follows. So I have given here an elementary introduction of this tau, but let give you a more detailed one. So this we will claim Ramanujan, we will say that we have seen already that this is an arithmetic functions. We will see its property. So consider this subset of complex plane, subset of complex numbers, only upper half plane above the real line. So this I am denoting by H. So those complex number whose imaginary part is greater 0. Yeah, so this is upper half plane, you can say. And I am writing this q is equal to e raised to the power 2 pi I z. For any z in upper half plane, write this. And consider this series, consider this function, you can say delta z is equal to q times, q is already given here, e raised to the power 2 pi I z, and this infinite product n equal to 1 to infinity, 1 minus q raised to the power n, and this power 24. And you can expand this again, right? This can be written a power series in q. This can be written as a power series in q, where q is e raised to the power 2 pi I z. So tau n q raised to the power n. So that tau n and this tau n, you can relate this now. So Ramanujan calculated this first 30 values of this tau n. So already this tau n is equal to 1, tau 2 is equal to minus 24, we have seen, tau 3 is equal to 252, tau 4 is minus 1472, tau 5 is 4830, tau 6, and then tau 30, you can say. And here you can see this tau 2 and tau 3 is equal to tau 6. Tau 2 into tau 3 is equal to tau 6. Or whatever you can, another you can see this tau 5 into tau 6 is equal to tau 30. So you can see that, you can guess that this is going to be a multiplicative functions. Multiplicative function means tau mn is equal to tau m times tau n, where whenever m and n are co-prime. So yeah, so Ramanujan calculated few values but he conjectured, you can say, he suspected that this function tau is multiplicative, that tau mn is equal to tau m times tau n. So he conjectured, even he made a conjecture that this tau is a multiplicative function, and this model proved in just after 1 year, 1917, that this in fact tau is a multiplicative function using tools from the complex analysis, because you can see these are functions, complex valued functions. So and then these are the coefficients. This is called Fourier coefficient in more general term. So this multiplicativity proved by this model. So you can see benefit of this multiplication, this multiplicative property. If you know a value at the co-prime integers, then you can, I mean, you don't have to calculate the value at 30, because if you know the value of 5 and 6, then directly this tau 30 is tau 5 times tau 6. So you can see the benefit of this if function is multiplicative. And this is proved by model. But so this is the first conjecture. Ramanujan made another two conjecture. Ramanujan makes another two conjecture for this tau functions. And what are that? This is another this one, that this is called recurrence relation. You can see this is that tau of p raised to the power r plus n can be given in terms of tau raised to the power pr. Means if you know the value of tau p, then you can calculate the value of tau p squared, tau p cubed, tau raised to the power p raised to the power 4, and so on. So tau p raised to the power r plus n can be given as tau p times tau p raised to the power r minus p raised to the power 11 tau raised to the power pr minus 1. So that's why if you know the value at tau p, then you can easily calculate the value for tau p squared, tau p cubed, and so on. This is only for prime. So this is and second conjecture. And third conjecture, this is about the bound of tau. This is conjectured by Ramanujan, that this tau p modulus of mod of tau p is less than or equal to 2 times p raised to the power 11 by 2. Means you can see if you hear values, this tau value, this is increasing, correct? Tau p and all these things, but it says that this tau p bounded by this p raised to the power, means these coefficients are bounded in the terms of this. Tau p is less than or equal to 2 times p raised to the power 11 by 2. This is true for all primes. I mean, till now, I mean, that time he made conjecture. So again, this model proved the first conjecture about multiplicativity, and this here first one, this recurrence relation, and this Pierre de line proved the second conjecture in 1974, more than 50 years, correct? More than near about 60. So these two proved, I mean, just after making the conjecture by Ramanujan. But this one is the toughest one, and conjecture was made in 1916, but this Pierre de line proved this conjecture about this bound of tau in 1974, after near about 60 years. And how this using heavy machinery from algebraic geometry. Deligne used to prove this second part using algebraic geometry, something called Weil conjecture, and he got field medal for this proof in 1978. So this is about this conjectures and its proof. Now another conjecture in this direction, you can see how interesting is this tau functions, Ramanujan tau functions. This conjecture is given by Lehmer, that tau n is not zero. Tau n is non-zero for every n. If you calculate the value, tau n is never zero. And various mathematicians has shown that, using maybe computer or something, that tau n is non-zero for all n less than 10 raised to the power 20. You can imagine this. But if you want to say that tau n is non-zero for every n, when you need a proof, correct? You need a proof, because still this is a finite number. So tau n is non-zero for finitely many one, but if you want to show that tau n is not equal to 0, you need a mathematical proof. So one needs a proof which is still open. Lehmer conjecture is is still open. No one knows that whether this is non-zero. But this is conjecture. Now, another result in this direction. So define this. So we have defined already sigma n, sum of the divisors, but you can define another arithmetic functions for every k, positive k, sigma kn, which is kth power of the divisor. So d is the divisor and take the kth power and the sum. So this function is the sum of the kth powers of the divisors of n. Then tau n, then tau n and this sigma k are related. How they are related? Tau n is equal to 65/756 sigma 11n. 11n means sum of the 11th powers of the divisors of n plus 691/756 sigma 5n minus 691/3 summation sigma 5k sigma 5 and minus k, where summations from k equal. Only I want to say that this tau and this sigma both, so sigma already everything about the sigma, and this tau and sigma, they are related. But this is the theorem by Ramanujan that the difference between tau n and sigma 11n is always divisible by 691. This is a theorem of Ramanujan. He observed that difference of tau n and sigma 11n is divisible by 691. That, I mean, that can be seen using this identity, correct? If you tau n minus this things is divisible by 691. That's so using this identity one can see. This is a theorem by Ramanujan. Another remark about this tau function is that one can observe, if you can see this tau functions, that 23 divides tau 5, 23 divides tau 7, 23 divides tau 11. But in fact, not always 23 divide tau p. So this is tau of primes. So in fact, for half of the prime p, tau p is divisible by 23. So 23 will not divide always tau p, but half of the prime, you can say. You can, so yeah, in some sense, half of the primes it will divide 23. And this can be explained something modern mathematics, you can say, yeah, something called Galois representations theory of Galois group. So that is difficult to understand here, but conjecture of Sayre says that there exists a representation rho, and those who know the Galois group of field extension, so there exists, I will say only 2 lines, so don't worry. There exists a representations of the Galois group. So this is absolute Galois group. Cube R is the extension to this. So GL2, you can say 2 by 2 matrices with coefficient in ZP. ZP is, you forget what about ZP, but you can think this is 2 by 2 matrices such that, so if you take row of any element from Galois group, so row of this you will get some matrix image, you will get some matrix, and then there is a trace. So trace of rho sigma is equal to tau p. So this is conjecture of Sayre, and later that this is proved by I think Chandrasekhar Khare and others. So using that, one can explain this many things about this tau functions, yeah, because this is related. Now, can p divides tau p? This is another question. Can p divides tau p? Like 2 divides tau 2, 3 divides tau 3, 5 divides tau 5, 7 divides tau 7. But then no prime p divides tau p up to a million. So up to 7, you can see 7 divides tau 7, but 11 will not divide tau 11. And you can go on, you can check, but it says that if you can check up to a million, prime up to a million, no prime p divides tau p except this one. Except this one, 2411 will divide tau 2411. So you can check up to a million, you will get only these 4, 2, 3, 5, 7, and then 2411. This is also an interesting observation. And then mathematician Newman in 1972. So are there any other prime? So yeah, this is so are there any other prime in 2010? This is a big prime using computer. I think someone has found this p. This is a prime 775833763, and this prime divides is tau of that prime. So you can see how and interesting these are numbers. Yeah, so this is about the tau, this Ramanujan tau functions. I want to say one more things about the tau functions. This is called Sato-Tate conjecture. Now it is a theorem. So already we have seen this tau p, mod of tau p is less than or equal to 2 raised to the power p11 by 2. But if you divide by this 2 raised to the power p11 by 2, then this will be in the interval -1 and 1. So this number will always be in this interval -1, 1, correct? For every prime p, whatever the prime p will take, this number will always lie in this interval. And this Sato-Tate conjecture, I have written not in a very technical way, very simple way, that this is equidistributed. There is some meaning of what is mean by equidistributed, but you can imagine what is meaning by this. So these are various prime, these are the numbers, various prime, these are the numbers like p equal to 2, p equal to, and they are equidistributed in this interval. Yeah, means not only at some point they are distributed, but equidistributed, both sides from 0. Yeah, but here you need some major theory and all these things, but this is not a full statement. But yeah, this is just make a sense that this number is equidistributed here. So these tauians are important, and one can generalize this tau to some another function, that is that's coming picture here, theory of the modular forms. Theory of the modular forms, which is very important in the number theory. So what is the modular forms? So you can think this SL2Z. SL2Z is the set of 2 by 2 matrices with coefficient in Z and determinant is 1. And you can consider already upper half plane. So if you write if Z in the upper half plane, then AZ plus B upon CZ plus D is also in the upper half plane. This is a simple exercise you can take. And a modular forms of weight K is a holomorphic function on this upper half plane. So you know already analytic function are holomorphic functions. So a modular form of weight K is a holomorphic function on upper half plane with some extra properties. With some extra properties, we satisfy this. And whatever we have discussed, delta, which is given by Ramanujan at that time, this is a modular form of weight 12. So there are many modular forms, and this is just one example for which Ramanujan studied this, and his Fourier coefficient. This one can, so this is now complex valued function. One has a Fourier expansion for this, and these tauians are called Fourier coefficient, and Ramanujan has studied this. But this is one example of the modular forms. So now there is a well-developed theory of modular forms and something called automorphic forms, and many people are studying this one. So yeah, using that you can so given this modular form, you can define L functions like here fz. So delta z is one example of f, and you have seen this delta z can be written as summation an raised to the power qn or tau n raised to the power qn. Similarly, any modular form can be written as an raised to the power q raised to the power n, and this an is called Fourier coefficient like tau n. And then it is all you can study these coefficients like tau n. One can study these coefficients, how they are bounded, what are their arithmetic property, and all these things. One can define L functions, and this is so if you take an is equal to 1, then you got this original Riemann zeta functions. Yeah. So yeah, this is about this modular forms and delta functions. Here delta L delta as a special case, you will get this one. Yeah. So any questions about this? Anyway, we can take questions later. if you have. So this is one work of this Ramanujan, or related work of the Ramanujan. Another one is the partition function. Already you have seen in the previous talk, but let me also again say. So the function, so Pn for any natural number n is the number of way of partitioning n. How many ways one can partition n? For example, 2 can be partitioned in 2 ways. So 2 is equal to 2 or 1 plus 1. 3 can be partitions in 3 ways. 3, 2 plus 1, 1 plus 1 plus 1. 4 can be partitions in 5 ways. 4, 3 plus 1, 2 plus 2, 2 plus 1 plus 1, and 1 plus 1 plus 1 plus 1. So this means P1 is equal to 1, P2 is equal to 2, P3 equal to 3, P4 equal to 5, P16 equal to 231, and so it's grow very fast. N is n is very small, but its Pn grow very fast. And already you have seen a generic functions, how one can calculate for at least this value Pn using this infinite product. So this side you can, right hand side you can expand, right, in terms of series, in terms of x raised to power n, and whatever the coefficient is, that is, you will get Pn. But this is not a formula. Can we have some formula for En? Like if you put n equal to 1, you will get P1. If you put n equal to 2, like we need some formula. And in 1918, Hardy and Ramanujan discovered this formula. This is just a problem. You see, this is very accurate one, but this is not exact one. This is, so Pn is approximated by this formula. So you have seen in sort of talk that this is omega n, Wn, whatever. So this is Pn is the number of partitions, and this right hand side is omega Wn. And you have seen that they are almost they are equal, because but for large value of n, when n tends to infinity, they are equal. They are equal means this tends to 1. That is the meaning. Pn upon Wn tends to 1 as n tends to infinity. So for large, when you take the large n, then this Pn and Wn are going to be the equal one. That is the meaning, that this ratio is going to be the 1 for large n. But one needs exact formula, but in 1937, this Hans Ramanujan derived an expansion for Pn, this complicated formula, very complicated. You can see here, Pn can be given in terms of this infinite series, which involve this Akn and their derivative, and there is sine hyperbolic, where Akn again, this is exponent sum of e raised to the power pi I, some Smk, where Smk can be defined in terms of this finite sum of this chord functions. Yeah, so this is the complicated one, but they have got this exact formula. Here, this is approximated one, but that is also very almost for useful, that is more useful, you can say, because this is complicated one. So another contribution related about this quadratic form. What is this quadratic form? So in 1770, Lagrange shows that every positive integer can be expressed as a sum of 4 squares. Every positive integers can be expressed as a sum of 4 squares. Like every positive integer cannot be expressed as a sum of 2 squares and sum of 3 squares, correct? Like 3 cannot be expressed as a sum of 2 squares. 3 cannot be expressed as a sum of 2 squares. Similarly, all positive integer cannot be expressed as a sum of 3 squares. You can get example very easily. But if you allow 4 squares, then every positive integer can be expressed as a sum of 4 squares. That is the question here. So this is shown by Lagrange. That means if you put A, B, C, D, then image you will get every natural number. If you put A, B, C, D integers, then image you will get all the natural number. That is the point here. So this is a very special case of quadratic. So quadratic form you think as a homogeneous polynomial of degree 2. I mean, I am not defining here quadratic forms, but you think them as a homogeneous polynomial of degree 2. And question is there any other quadratic form which represent all positive integers? Like this represent all positive integers. A square plus B square. You just put the value of A, B, C, D, you will get all the positive integers. Is there any other this kind of quadratic form which gives all positive integers? And in 1910, Ramanujan gave 55 more examples. Like this already you have seen. This represent all the integers. This will also represent all the integers. This will also represent all the integers. You know, this A square plus B square plus C square plus 7D square will also represent all the integers. But interesting part is that you know, A square plus B square plus C square plus 8D square does not represent all the integers. So you can see here Ramanujan gave 55 more examples which represent all the integers. So, you know, this Ramanujan was inspired this, that is called the 15th theorem by Conway and Seeberger in 1933. It says that, so here is some technical language, but you can ignore that. A positive definite quadratic form with integer matrix. So every quadratic form can be given by some matrix. So a positive definite quadratic form with integer matrix represent all positive integers. If you represent all positive integer up to 50, it says that suppose I am checking this one whether this represent all natural number or not. So if it represents number up to 1 to 15, if we can check only that whether this represent 1 to up to 15, then this theorem says that if you can check that this represent up to 15, then this will represent all natural numbers. Yeah, so this is very important theorem. And you know, this is the starting point for some of the Manjul Bhargava work, very famous mathematicians of Indian origin. So Ramanujan, these ideas has inspired and continue to inspire in future, like this Deline proved this Weyl conjecture, and using that he got this bound tau p, and he got field medal in 1978. Then this proof of Fermat's last theorems also related with that. And there is a Langland program, which is this generalization of modular forms and automorphic forms, and all these are you know, gave, so Ramanujan work gave this various directions up to the modern mathematics. Many people are working in that area. And in the end, I want to say that this about this Ramanujan illness and this famous taxi cab numbers. So in 1917, this Ramanujan contracted this tuberculosis during his stay in England, and but he showed some improvement in 1918 and was elected to the Royal Society for his contribution to the mathematics and mainly number theory. In 1919, he returned to India and shortly afterwards passed away in 26 April in 1920 at the very early age of 32. But famous number is 1729. So when Ramanujan was ill, he was admitted in hospital, and Hardy came to visit him in a taxi, and on entering this Ramanujan room in the hospital, Hardy remarked that I just came in a taxi numbered 1729, which looked like a dull number. I hope it is not a bad omen. This Hardy says to Ramanujan. Immediately Ramanujan replied that on the contrary, it is very interesting number. It is the smallest number that can be written as the sum of two cubes in two different ways. Yeah, so this 1729 is the smallest number that can be written as sum of two cubes in two different ways. That is the property that is the smallest one. What is that? 1729 is 1 cube plus 12 cube and 9 cube plus 10 cube. So this is called taxi cab numbers. Yeah, so thank you very much for paying attention. I will stop here.
Thank you, sir. Thank you so much for sharing the contribution of Ramanujan sir and in number theory. Any participants who want to ask the question? Am I audible?
Yes, sir, you are
Anand
audible.
sir? Okay. Any participants?
Yeah, any student want to ask?
There is one question. I think that is only looking me. And Vineet sir, you are seeing that question. Priyesh Tayal have asked, sir, it is mandatory to be an integer matrix.
Where?
No, sir.
Priyesh, are you hearing to us? You can unmute yourself and you can ask your question yourself to sir.
In this one, the 15th theorem, the positive definite quadratic form.
Yes, sir. Yes, sir. In the 15th theorem.
Yeah, so this is, you know, so this quadratic form and there is those who read this linear algebra, this bilinear form and quadratic form, there is a bijective correspondence, and a bilinear form can be represented by a matrix, yeah, symmetric matrix. And here I am saying, so yeah, so theorem is that positive definite quadratic form with integer matrix means
Okay, sir.
quadratic form which can be represented by this integer matrix.
Integer. Okay, thank you, sir.
Any other question? You can ask directly. No need to write the question in chat box.
Yeah, you can ask here.
I think no one have the question. So thank you so much, sir. And the final, I think so, the last. So it is my immense pleasure to deliver the vote of thanks for this national webinar to all our dignitaries assembled here. First of all, I would like to thank to all our respected guest speakers, Dr. Saurabh Kumar ji and Dr. Mahan Kumar Verma ji, who have spared their precious time to enlighten our participants. Thank you, sir. Thank you so much. And I would like to thank to our principal, sir, Dr. Gyantosh Kumar Jha, sir, for his guidance, support, and encouragement. And also thanks to our IQAC coordinator, Dr. Vinita Tuli ma'am, who always motivate us to organize such kind of webinars. And thanks to all our participants for taking part in this national webinar. And last but not the least, I would like to thank all the other faculty members of Mathematics Department, IRSD College, for their cooperation. Thank you so much. Thank you so much. Thank you, sir. Mahan sir, thank you. And कोशिश करेंगे कि next time भी आपसे offline में मुलाकात हो. बहुत अच्छा लगा.
Thank you so much, Mahendra sir. In the last, I would also like to thank our technical handling Anand ji.
Sure.
Anand ji have handled very nice way this session. Thank you, Anand ji.
Thank you.
Thank you, sir. So Anand ji, you can end this session.
Okay, thank you.
Okay.
Thank you.